So yeah, I want to thank the organizers for the great job they did with this conference. And then I want to highlight that my presentation has two parts. The first part is in collaboration with Yanni Twinketa, Rob Jack, and Ludovic Berthier, and it's about active matter. And the second part is about non-reciprocal interactions and is a work with Ludovic Berthier. And both of these topics go under the title Emergence of Mesoscale Flows under Non-Equilibrium Drive in Crowded Environments. So because active matter has been introduced in this conference already before, I will go very fast. So here's an example of an experimental active system, the walking grains from Olivier Duchot, which can self-propel, meaning move persistently, like you can see here in the dilute case, where they are basically non-interacting. And what we are typically interested in are the collective phenomena that emerge when you put many of these particles together. And I personally, I'm especially interested in the phenomena that emerge at high densities, like here. But the phenomenon that I want to talk about today is also already appeared in the conference, is called active turbulence, bacteria turbulence, or there was one more, mesoscale turbulence. And here's an example of this. It's a system of rod-shaped bacteria where you see the formation of streams and flows and vortices. You can here see the snapshot of the vorticity. And this kind of turbulent-like looking flows has been observed in a large variety of active systems. And I just show you one more example of a very different system. This is a monolayer of epithelial cells, where you can see the same kind of emergence of mesoscale flows. Now, if you look in details, you might find differences, but having this phenomena emerge over and over again in all these different experimental systems can motivate us to ask the question if active turbulence is a generic phenomenon of active matter, and if it is so, then it should also appear in the minimal models of self-propelled particles. Now, these references I'm listing here to say that I think there were already lots of hints in the literature. Chandan was talking about this work, showed the phase diagram, that these flows indeed emerge in the minimal models, but it's difficult. And I want to focus on why it is difficult. And for this, I first define what I mean with minimal models. And I'm really talking about just active Brownian particles, active Ornstein-Uhlenbeck particles. These particles have a unit vector assigned to them that has some orientation theta. And then when you look at the equation of motion, these particles simply move with a constant velocity v0 in this direction given by the unit vector n. And now if theta would never change, the particles would just keep moving forever in the same direction. But typically, the orientation diffuses in time with a typical time scale, which is the persistence time, tau, such that they move for an average time, tau, in the same direction before they change their direction of motion. Now, again, we are typically interested in the collective phenomena, so we would like to add some steric interactions and maybe also some thermal noise. And this model has been studied intensely by various groups, and the phase diagram has been computed. And here I'm showing you one example which has been computed for this active Brownian particles to illustrate why it's difficult to find these flows, essentially. On the x-axis, you have the density. On the y-axis, you have this V0, so somehow tuning the persistence of the particles. And then you have different phases in the system. You have a liquid phase. Here, the largest phase, then at large densities, the particles, it's in 2 dimensions. So they will go in an arrested phase where you have some degree of positional order. And if you increase the persistence of the particles, you will end up in this phase-separated state, which is called motility-induced phase separation, and a purely non-equilibrium phenomena, because this phase separation appears between particles which are purely repulsive, and in equilibrium you need attractive interactions for this kind of phase separation. Now, where in this phase diagram could we find particle flows emerging from spontaneous velocity correlations? So that, of course, must be there. And here, for me, velocity is the r dot in the center of mass motion-corrected frame. So where could we find these spatial velocity correlations in this phase diagram? And for this, you can look one more time at this equation of motion. You know from equilibrium that these kind of correlations will not emerge from steric interactions alone, and they will also not emerge from the self-propulsion forces alone because they are strictly independent between different particles and hence independent in space. So they can only emerge from a competition between very persistent active forcing and crowding at high densities. So in other words, we are looking for a highly persistent dense fluid that where crowding effects matter. And really the only place where you can find this in this phase diagram is this tiny little liquid corner here. But this is not very persistent. We would like to push this liquid corner here up to higher and higher persistences to observe these flows. And this is actually possible because this phase diagram is just one slice of a much higher dimensional phase diagram. There's at least one more axis that you can put, which is this persistence time tau here. And then if you like, you can also put temperature. And this is the work, PhD work of Jan Edwin Kitter, that he managed to find a way how to slice this phase diagram in a way that you can indeed extend this liquid corridor to arbitrary large persistences. And this is the phase diagram I'm showing you here. So you have this liquid corridor between this phase separated state and the arrested phases. And I should mention that this is a phase diagram for athermal active Ornstein-Uhlenbeck particles. And also an important detail is that the particles are polydispersed to frustrate this emergence of order here, which makes also the appearance of the flows be a bit easier. Now, what we did, so if you want to have details how this phase diagram is precisely sliced, I can talk to you in person. But what we did together was we explored this corridor and looked at the characteristics of these flows that I'm showing you here. So this is these emerging mesoscale flows in a system of active Ornstein-Uhlenbeck particles. I want to highlight again the fact that in this system, it's finite persistence time. And there's absolutely, so this color code here is the orientation of the self-propulsion forces. And you can see that there's absolutely no ordering at small scales and at large scales. The the self-propulsion forces are completely uncorrelated in space. Now, we could measure many things in the system. Here is a snapshot of the vorticity, and here a snapshot of the velocity field. The color code is the amplitude of the velocity, where you can see it's highly heterogeneous with slow and fast regions. But I don't want to go into the details of these flows because the next system I will present to you has the flows we observed there have extremely similar characteristics. So you would basically look at the same graphs twice, and I don't want to do that. So from this part, I want that you take away that active turbulence is indeed a generic phenomenon of the minimal models of active matter. And the lengths and timescales of these flows can be scaled to arbitrary size by moving up in this corridor between this MIPS and the arrested glass. Now I come to the second part, which is about non-reciprocal interactions. And for me, the motivation to study this came really from active matter because non-reciprocal interactions are widely present in active systems. In this system, there are at least two kinds of non-reciprocal interactions. The first one, which is the most obvious one, is the predator-prey interactions, which can be thought of. The predator is attracted to the fish, but the fish is repelled by the shark, so it's non-reciprocal. But another non-reciprocity emerges also in the single species itself of the fish. They have alignment interaction to swim together in a similar direction. And this alignment interaction works through vision, but the vision is limited, so the fish can only see the neighbors in front of them, but not the neighbors behind them, such that, again, these alignment interactions are non-reciprocal. Now, the non-reciprocal system that I want to study is motivated by this situation of dense crowds, where you could argue that self-propulsion might not play such a role anymore because the system is too dense. And non-reciprocal interactions might be more important, that either come through vision or also when you look at our body, it's asymmetric with our feet. we might react to pushes that come from the front, different to pushes that come from the back. So this is just a wide motivation for the model that we study, which looks like this. So you have particles that have, again, a orientation, which is, if you like, the orientation of their vision. And then the forces with which the particles are repelled are modulated by how well they see their neighbor. So you see that this particle here forms a rather small angle with its neighbor, so the line joining the particles, the neighbor, which means the particle sees this particle rather well, so it's strongly repelled by the neighbor, whereas this particle here has a large angle, so it means it doesn't see its neighbor so well, so it's less strongly repelled. The force that does this kind of interaction for us looks like this, so it doesn't depend only on the interparticle distance, but now also on this angle alpha that is formed between the orientation and the axis joining the two particles. And this angle alpha enters in this term here, so otherwise there's just a normal gradient force. And this alpha does that when a particle is in front, again, it's strongly repelled, and when there's a particle behind, it's not as strongly repelled. And the nu here, that will tune my non-reciprocity. If nu is 0, it's an equilibrium potential. So for the steric potential, we use just purely repulsive WCA potential with short-range interactions, and the equation of motion looks very simple. So the particles only move due to the steric non-reciprocal interactions. And what we do in the beginning is, so the orientation of the particles doesn't evolve in time, it's quenched. And then this means we have to be careful with how we distribute the orientations initially. And we choose uniform distributions of the angle just to reduce the center of mass motion of the particles. And then again, they are polydispersed to frustrate the emergence of our order. Now, I want to highlight that there's no activity in the model, and motion emerges only from the non-reciprocal interactions. And of course, if nu is 0, the particles will force balance, there will not be any motion. But if mu is very large, you can imagine that the particles constantly are more repelled from the front than from the back, so they will roughly move just backwards towards their direction. And the interesting thing is when mu is in between these two limits, where particles move rather independently and where they don't move at all. And in this intermediate regime, we indeed find again the emergence of these turbulent looking flows, where here I just colored some particles black so that you can trace them more easily. Here's again a snapshot of the velocity field, where you can see again the emergence of vortices and streams of various sizes, and then again the amplitude of the velocity is highly heterogeneous with fast and slow regions. Now, there are lots of similarities between these two systems, but there are also differences. When you, in this system, what we can do is we can reduce the non-equilibrium drive up to a point that the non-reciprocal forces cannot push the particles in these flows for arbitrarily long, but they find some force balance state. And it's not like an equilibrium force balance state where particles stop moving completely because the interactions are non-reciprocal. But here what you see is that I start the simulation from a random initial configuration. There are some initial rearrangements, but then the rearrangements stop. And the system finds a non-equilibrium force balance state by all particles feel exactly the same force, and they drift like a block in some arbitrary chosen direction. Now, between these two different states, so absorbing states and mesoscale flows that continue for forever, there is evidence for a phase transition, where here you see this parameter of the non-reciprocity on the x-axis, and on the right side is the time scale of these turbulent-like flows that diverges, and on the left side is the average freezing time that I can measure by starting the system from independent random initial configuration, and that also diverges very fast. Now, what I want to do in the following is I want to characterize this phase transition, and I want to argue that maybe it falls in the universality class of conserved-directed percolation. And the question mark is there because this is ongoing work, and I might change my mind later about this fact. A small remark is that this phase transition washes out if there is a finite persistence time, which, yeah, if you make it a correlation to the active systems there, we can't take the infinite persistence time limit, so we cannot see this, this transition. So I will start characterizing this transition here by looking at particle displacements. So here you see the particle position at t equal to 0 of some particle. It's the same particle at a later time at a different position. And typically we look at the mean square displacement. What we do here is we decompose the displacement of the particle in a component that is parallel to its orientation and in a component that is perpendicular to the orientation. And that is useful, which you can see here. So I'm plotting this different mean square displacements for some values of the non-reciprocity. And the first thing that you see is that the system slows down when the non-reciprocity reduces. So it's just meaning that I'm reducing the non-reciprocal drive. And then you see that the two quantities are equivalent, quite the same. They grow in the same way, but not for all times. At large times, they become different. And these curves, they are quite interesting. So they are ballistic at small times, then they decorrelate and try to become diffusive, but they don't manage at some time scale. Then they become ballistic again, and then at even larger time, they try to again decorrelate, where only now the perpendicular, the transverse mean square displacement will really stay diffusive, but the longitudinal mean square displacement will again become ballistic. And this is just due to the fact that the particles never change their orientation. Now, from these curves, I can extract a number of quantities. And of course, you know that the mean square displacement is directly related to the velocity autocorrelations. And this kind of shape of the mean square displacements really corresponds to a two-step decay in the two-step exponential decay of the velocity autocorrelation, where then we have, I can fit this two-step decay to the velocity autocorrelation and extract timescales. The first timescale is the interparticle collision time, which decorrelates at small times. And then there is the second timescale of the flows, which is the second decorrelation event here. And then there is this long time ballistic velocity, which is the ballistic part here for the longitudinal mean square displacement. So I can obtain these two timescales, and I can check how these timescales grow as I approach the transition. And I find a critical exponent that is indeed compatible with the conserved-directed percolation. And then I can, from this curve, I can also extract a short time velocity and this long time ballistic velocity. And when I rescale this long time ballistic velocity by the short time one, which is just to filter out the trivial slowing down of the system, I can see this as an order parameter. And then also here, I find a critical exponent that matches with the conserved-directed universality class. And it's not really obvious what order parameter to use, or you can make different choices. Here's another example where I get, it's always based on the velocity somehow, where it's also matching with the conserved-directed percolation rather well. Now, the last point that maybe a quick remark, that for the active Ornstein-Uhlenbeck particles, the mean square displacement and hence also the velocity autocorrelations, they look very similar to the transverse mean square displacement, means the part that becomes diffusive in the end, because in the active Ornstein-Uhlenbeck particles, the persistence time is finite. And this second time scale, the time scale of the flows, is set for the active Ornstein-Uhlenbeck particles by the persistence time. So there we can again scale the time scale of the flows by increasing the persistence time. Now I come to the spatial correlations, and when we talk about turbulence, we like it's not turbulence. I mean, they chose this word turbulence. It's not me who chose it. But they look at the kinetic energy spectrum, which is just the Fourier transform of the velocity field, which I'm plotting here for you. So in this Fourier transform, there is, you see that there is a maximum in the curve. And this maximum k, that sets, or that defines the correlation length, because here on this side, you see that on the left side for small k, the curve grows linear with k. And if you look at the definition of the mean square of the energy spectrum, it just means that you see this growth coming from this k here, and it means that the Fourier transform of the velocity field is independent of k. So there are no correlations anymore. So that means the real space correlations are uncorrelated for length scales that are larger than given by this k maximum. And then on the other side, you find that the energy spectrum decays with a specific power law, and this corresponds to real-space correlations that decay as r to the power of -1/2. Now, people look a lot at these exponents, and this exponent here is very similar to the one that we find in the active systems. So the energy spectrum basically looks quite the same. What we can do here now, because if it's a phase transition, then there should be a unique curve that we can collapse these energy spectra to. And I'm choosing here I'm dividing the energy spectrum by k. And then I'm normalizing this by the value it should have at k equal to 0. And then I'm just dividing by the x scale by this maximum position in the energy spectrum, the maximum k. Then you see that the curves really fall perfectly on a line. I can collapse the curves, and I get again this exponent of -1.5, which is corresponding exactly to this -0.5. And what I can extract from this collapse is this length scale, k, and I can check how this length scale scales as I'm approaching the transition. And again, this length scale is completely compatible with what you would expect from the critical exponent of conserved directed percolation. And now, yes, I already said this. Here for active Ornstein-Uhlenbeck particles, again, this length scale of the flows, they can be tuned by increasing the persistence time. And it looks very similar. Now I come to the summary of this work. So what I have shown you is that the mesoscale flows can spontaneously emerge from a competition of very persistent active forcing and crowding at high densities in the minimum models of active matters. The time and length scales of the flows can be tuned to arbitrary large sizes by increasing the persistence inside this liquid corridor between the MIPS and the arrested phase. What I forgot to add here is that when you look at the decay of the energy spectrum, many people have looked at this in the other systems, and we really find an exponent that is much smaller than what has been observed before. So arguably opening up a new class of active turbulent systems. And then from the non-reciprocal system, which is really an ongoing work, I've shown you that the same kind of flows can emerge with very similar properties when the persistent non-reciprocal drive competes again with the crowding at high densities. But then in contrast to the active systems, I showed you that there is a presence of an absorbing phase transition for infinite persistence time of the orientation of the particles that shows critical exponents that are in agreement with the conserved directed percolation universality class. With this, I want to thank you for your attention.
Very much, Juliane, for the nice talk. In the second part, you said that you need to be careful with the initial conditions. Would you go as far as saying that your system is dependent on the initial conditions and that you have some kind of memory, like everlasting memory of initial conditions, or
no,
is it going too
the
far?
remark was rather, so in the system, it's really, it's tricky to reduce the center of mass drift of the system. And this is all that I wanted to say. So you can, in principle, just sample your orientations initially that are frozen then. So what I do is I have n particles, and I divide 2 pi by n so that I know that the center of mass motion should be really as small as possible. Now I could also sample the angles from a distribution, which means that if I have a finite number of particles, there will be, the distribution will not be perfect. And then I have a larger drift, but that doesn't destroy the transition or anything. And I can also artificially tilt the distribution, and it's there.
Yeah, I'm sure you told us on the way, but what is the nature of the absorbing phase?
I'm not sure what you mean with the nature.
I mean, like in other contexts, absorbing phases are very simple and they're empty or something like that. You know, but what?
So the nature of the absorbing phase here is that the particles find configuration where they are force balanced, and force balanced means that each particle feels exactly the same force, and they can't escape from this configuration. So it's really an absorbing state.
Thank you.
Yeah. Oh, you got a mic.
Yeah,
All right.
I got a mic already. Yeah, I had a question on the first part of your talk.
Yeah.
Where you show this simulation that are supposed to happen in a very narrow area. And so I expect you need to have very precise simulation to have that. And so you didn't give any details on the simulation you're doing. If you're doing some discretization of some SPD schemes or this type of thing, because I expect it's hard to control the errors in this type of schemes.
I mean, we tried different things. We also tried different simulation schemes. Some that should be more precise than others, but it's actually not as fragile as you might think.
Last question, Deepak.
So you said the velocity of the correlation function has an exponential decay. That's very surprising because there are all kinds of hydrodynamical effects. So you don't get any hydrodynamical tails in the velocity autocorrelation function?
I said there's a exponential tail. So they are, there is a scale-free part, and beyond that they decay exponentially. Yes.
Okay. No, momentum is not conserved. It's only number is conserved. Okay, let's thank Juliane once more for a great talk.